This is CS50, Harvard University's Introduction to the Intellectual Enterprises of Computer Science and the Art of Programming. And this was apparently me around the time that I sat where you guys now sit, thanks to a teaching fellow who spent a little too much time trolling around Lamont Library, where the 1995 freshman registers apparently still are. And I point this out because this was a big deal for me back when I was a freshman and ultimately sophomore, considering to take a class like this, CS50, but more generally computer science. And if you, like me, have this perception of computer science from high school or even middle school, you might have the perception that it's entirely based about programming. It's perhaps a bit antisocial. It's perhaps the computer lab heads down, sort of coding away on something that you don't necessarily understand. And yet, I too had that perception freshman year. And this course, and dare say the field more generally, really did have this reputation to beware. I certainly assumed that most everyone around me certainly knew more than I did. And this wasn't just true of CS for me. This was true of most any field at Harvard in the course catalog that I had no familiarity with. And so I instead gravitated toward the more comfortable. I took a lot of gov classes and economics and history just because that's kind of what I knew and liked in high school. I wouldn't say I loved it, but I knew it, and it was within my comfort zone. And it wasn't until sophomore year that I got up the nerve to take this class, CS50, and I only did because the professor at the time let me take it pass-fail, now called sat-unsat. And that allowed me to get over this sort of mental hurdle that I had imposed upon myself, sort of fear of failure or simply not doing as well as I might have been accustomed to. And so I bewared a class like this until then. And I always kind of regretted not exploring earlier on. And that doesn't have to be this class, doesn't have to be CS, but can be really any field more generally. But those really were my takeaways around the time I looked like this. And I've taken comfort since in taking over this class and have found it inspiring that these days 68% of the students in this room and in this room last year had never taken a CS course before. So if you do have that mental model of everyone to your left and your right surely must know more than you, odds are it is not in fact the case. In fact, within CS50 we have these different tracks, different types of sections for students less comfortable, students more comfortable, and students somewhere in between. And there's no formal definition to these labels. You just sort of know it if you are. And if you kind of have one foot mentally out the door today because you're not really sure this is for you, you're probably among those less comfortable, but as such you're in the majority, 56% of last year's students. If, by contrast, you have been programming since you were 8 years old, 10 years old, whatever, but you're largely self-taught and therefore maybe have lots of gaps in your knowledge or don't really understand all the formalities, you just kind of figured things out, you might be among those more comfortable, and if not, maybe you're somewhere in between. And so in CS50 sections, do we have similar students together, similar comfort levels, similar backgrounds, so that everyone can kind of feel comfortable speaking up, not knowing things, and beyond? Because ultimately, the course is graded and assessed ultimately very much manually, very delicately with respect to students' prior background or lack thereof. Indeed, what's most important at the end of the semester is not so much where you end up relative to your classmates, but where you end up in week 11, our very last week, relative to yourself today in week 0. And in fact, thanks to CS50's own Haley James and a whole bunch of CS50's team members this summer, they spent a while traveling around the country bringing folks back to campus, alumni and former students and staff who had some connection taking or teaching CS50 in some form. And if you'd like to see stories of some of your predecessors and folks who sort of found their way accidentally even to computer science, finding challenges along the way, check out this domain that the team put together, project5050.org. Now, the course itself, ultimately, is not about programming per se. That's indeed a tool that we'll use. It's really about this. And that's really what CS is, the fields more generally. Whether you're studying hardware or graphics or theory or any number of fields, and artificial intelligence these days, machine learning and beyond, it's really just about solving problems. And what's really cool about CS, I found early on, is that it doesn't necessarily, it's not an end unto itself. It's this field that empowers you to go do more interesting, more powerful things in the humanities, social sciences, physical sciences, the arts, anything, because you have this new mental model for how you can solve problems better, more efficiently, how you can solve them correctly, and how you can sort of analyze large data sets or solve problems that might have otherwise been beyond your grasp. So what does this mean? What is problem solving? Well, we could perhaps distill it as simply as this: a big black box, some secret sauce, into which go inputs, like the problem we want to solve, and out of which comes outputs, the solutions that we want. So a very generic way of describing it, but what's pictured here in the black box is the so-called algorithms. And we'll come back to that in just a bit, the actual ingredients for solving problems. But how do we represent inputs and outputs. Odds are, even if you're not a computer person and don't really think like one, you probably know that computers only understand a very limited vocabulary. Like, what is the alphabet, so to speak, that they speak? ASCII maybe, but more binary. Binary. Bi meaning 2 for zeros and ones. So whereas we humans typically use decimal, dec meaning 10, 0 through 9 is in our alphabet of letters. Computers, of course, as you may have heard, only use zeros and ones. Now, why is this powerful? Well, it turns out as soon as you have at least 2 digits in your alphabet, you can start to represent things much more powerfully and much more efficiently. For instance, if I wanted to count the people in this room, how many of you could I count on just one hand? All right, hopefully 5. So I could count 5 of you. 1, 2, 3, 4, 5. But you know what? If I were a little more clever, I bet I could use the same hand and count as many as 32 or maybe 31 of you. Well, how is that? Well, right now I'm kind of using the unary system. Uno meaning 1. So it's just 1 digit in your alphabet, the finger or no finger. It's not quite the same as 0 or 1. So 1 person, 2, 3, 4, 5. But what if I instead permuted my fingers in some way so that the pattern of fingers that are up actually matters, not just the quantity? So maybe this is still 0. This now is 1. And instead of 2 being this, maybe 2 could be this. So if my second finger is up, I'm going to call that 2. And if my first 2 fingers are up, I might call that 3. Somewhat offensively, if just this finger is up, I might call this 4. And then 5. And then this gets kind of painful. 6, 7. And what I'm actually doing is counting in binary. Now, that might have looked completely cryptic. But it turns out as soon as you have 2 digits, that's enough to represent anything you want and to do so pretty darn efficiently. But why? So odds are, if you're like me, you probably grew up learning, of course, the decimal system, 0 through 9. And you might have written on the board some point like this number, 123. But why do you think of that as 123? It's really just a pretty pattern of symbols, glyphs, so to speak, on the screen that we ascribe some kind of mathematical meaning to, 123. But really, it's just like someone drew in ink on the screen some symbols. Well, if you're like me back in grade school, you probably learned that the rightmost number here is in the so-called what place? The ones place, right? And so if we wanted to label these things, we might put ones place there, and then, of course, the tens place, the hundreds place, maybe the thousands, 10,000, and so forth. So we had these sort of mental models for the columns. And notice they happen to be powers of 10. 10 to the 0 is 1. 10 to the 1 is 10. 10 to the 2 is 100, and so forth. So that's the pattern, even if your grade school teacher didn't talk about exponentiation at the time. So why is this number 123? Well, it's because we have a 1 in the hundreds column, so 100 times 1. We have a 2 in the tens column. We have a 3 in the ones column. And of course, if we start to do the arithmetic now, that's 100 plus 20 plus 3, or obviously 123. And all of us take that certainly for granted these days. You see a number, you know what it is mathematically. But computers fundamentally work in the same way. So even if you, up until now, have never thought of yourself as a computer person or had no idea really what it means for computers to speak just zeros and ones, all you have to do is update the places. Instead of powers of 10 for dec, meaning decimal, we're going to have powers of 2 for binary. So now we're going to have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Same idea, it's just a different base. We changed 10 to 2. And so now we have places like this, 1, 2, 4, and if we kept going, 8, 16, 32, 64, and so forth. So as such, what number is this on the screen in binary if you convert it in your head to decimal? It's just the number 1, right? Because you've got a 1 in the ones place, and then a 0 in every other place, so it's just 1 times 1 equals 1. Now, if I were using unary, or my hands, the sort of traditional way, 2 would be this, where you put up 2 fingers, but not if you're trying to use patterns as well as quantities. And so in binary, how do I represent the number 2? 0, 1, 0. It's the equivalent of putting up just my index finger here. And if I want to count to 3, now I need to add a 1 to the mix, so I add the ones place. And now, if you sort of start to visualize this, it's like one of those really old school clocks where the numbers flip around and roll over. Now those ones are going to kind of flip and become zeros, and the 0 is going to become a 1. And so now we have 5, and then 6, and then 7, and then, dang it, how does a computer count to 8? Yeah, you just need to add another place, right? Just like we humans don't have an infinite number of numbers when we write something down. We sort of stop when it's not necessary. All we need is another bit. We just need to add another 0 or 1 to the left, specifically a 1. Then all these ones can become zeros. And we can do this toward infinity. But where are these bits coming from? This is all very abstract and just pictures on a screen. Well, it turns out that we have fun physical ingredients, all of our computers. Maybe it's your laptop or desktop or your cell phone. At the end of the day, they're either driven these days by batteries or like a cord into the wall, where electricity comes from. And even if you have little familiarity with electricity, you probably know that it's like little electrons flowing. So there's some kind of physical resource that can flow or not flow. You can turn it on or off. Well, much like these desk lamps here, I have 3 physical lights. They're, of course, connected into the electricity, so I have some physical input. And now that I do, I can kind of implement my own computer using these simple desk lamps. If I want to represent some value, some input or output, OK, here's the 0. This is 0 in binary. I just need to leave 3 light bulbs off. If I want to represent a 1, I need to turn this on, and that's now the 1's place. If I want to represent 2, I just need to turn this light on. If I want to represent 3, this one comes on. If I want to represent 4, that goes on. 5, 6, 7. And then, of course, we need like 8 if we want to represent and turn these off 4 total bits together. And so that's all that's going on inside of your phones and your computers. Phones and computers and devices these days have what are called transistors, which are tiny little switches that are on or off. And that's all we need if we have some source like electricity to just store information. We just need lots and lots of switches, lots of light bulbs, certainly much smaller, in order to represent information. But computers, of course, can do much more than represent numbers. What about letters and emails and things like that? Well, for that, we actually need to kind of decide as humans how we're going to interpret things like these light bulbs. In one context, like a calculator, they might represent numbers, decimal numbers, whatever. But in an email program, Microsoft Word, Google Docs, you probably want those light bulbs or those transistors in the computer storing not just numbers, else you could just do math. You want them storing letters and sentences and paragraphs and so forth. And so we need to have some kind of mapping. And we'll do that as follows. ASCII, which is just an acronym describing a mapping from numbers to letters. Humans, years ago, just decided, you know what? In the context where we need letters, let's just store a pattern of bits that's equal to the number 65 if we want the letter A. Pattern of bits equal to the number, decimal number 66, if we want to store the number B. Fast forward to H and I, if you want to store H or I, 72, 73, and just store that many bits. And now I don't care anymore in this story how you represent 65 or 73. I just need to know that you can somehow, with light bulbs on stage, with transistors in my phone, or whatever the device may be. We can begin to abstract away these low-level details. In fact, we're not going to spend much time after today talking about binary and CS50, because here we have sort of electricity conceptually. On top of that, we can build the notion of binary, zeros and ones. And once we come up with this convention, now we can start to talk about letters of an alphabet. But that's not the only thing we can talk about. We can also talk about graphics and videos and all of the things we take for granted these days. For instance, and just to recap, what message have I encoded here on the screen, if you recall? Hi. Yeah, it's hi, because 72 and 73, I claimed a moment ago, are just the numbers we humans came up with years ago to represent HI. I don't really know what 33 is. You'd have to look it up or be told it. Turns out it's an exclamation point, because indeed humans decided to express in numeric codes as well all the keys on a keyboard. Unfortunately, they weren't very far-sighted early on. They only used 7 bits total, and later kind of 8 bits. But even that, even though that gives us over 200 possible values, 256, there's a lot of languages that aren't written in like the English alphabet, Asian languages and the like, that have many, many, many more symbols than you can express with just 7 or 8 bits alone. And so now ASCII has been succeeded by something called Unicode. And long story short, humans have begun to solve problems that were initially created by not anticipating needing or wanting even larger values than these. But in another context, like Photoshop or any graphics program, you might see the same pattern of bits, 72, 73, 33. But in those programs, they know to interpret these numbers as some amount of color. If you've ever heard of RGB, red, green, blue, this is just an acronym that describes how you can mix together 3 different colors, sort of in the spirit of paint, or more technically light, combine these 3 different colors, and get any color of the rainbow. So each of these numbers, I'll claim, can be from 0 to 255. And 72 out of 255, that's like a medium amount of red. That's like a medium amount of green, and just a little bit of blue. And if you combine those 3 colors by mixing them together into just one dot, or pixel, as it's called in a computer, you get this sort of murky shade of yellow. But in the context of Photoshop or some graphics program, that is what those same 3 patterns of bits would be interpreted as. And it happens to be the case that talking in terms of single bits, it's not all that useful. With 1 bit, you can count as high as 1. So humans long ago also standardized on a nomenclature. A byte, B-Y-T-E, is just 8 bits. And if you've ever heard of kilobytes and megabytes and gigabytes and terabytes and the like, those are just multiples thereof, typically orders of magnitude of 1,000 or 1,024 or more. So with just 3 bytes, 24 bits, can we represent letters, numbers, or the like? And ultimately, these are just examples of abstraction. And this is going to be a theme that permeates not just this class, but computer science more generally, taking very simple ideas that really don't seem all that interesting at first glance, but as soon as you use them as ingredients to solve a problem, you can then sort of reuse that tool to build something more interesting, reuse that tool to build something more interesting still, until you get to work with application development and solving real problems that you care about, taking for granted that people that came before you have solved a lot of these lower level implementation details, so to speak.